Today we're diving deep into the science that's changing the world of IVF. We're talking about Preimplantation Genetic Testing, or PGT. It's this incredible tool that lets us peek at an embryo's DNA before it's ever transferred to the uterus. So let's unlock that blueprint.
So if you're going through IVF, this is the question, isn't it? You might have a few embryos and they all look great under the microscope, but how do you really know which one has the very best shot at leading to a healthy pregnancy? That's exactly the problem PGT was invented to solve.
And here it is. PGT is basically the umbrella term for a whole suite of tests. They all work by analyzing a few tiny cells from an embryo to check for specific genetic issues. This gives everyone involved, the doctors, the parents-to-be, a whole lot more information to work with. Remember, PGT isn't just one thing. It's a whole family of different, super specialized tests.
Okay, so here's our game plan. We'll kick off with PGT-A, which is all about counting chromosomes. Then we'll get really specific with PGT-M, the one that hunts for single-gene disorders. After that, we'll tackle the complex world of PGT-SR for structural issues. And to wrap it all up, we'll look at the big challenges and what's coming next for this technology.
All right, first up, PGT-A. That A stands for Aneuploidy. It sounds complicated, but it just means having the wrong number of chromosomes. And this is easily the most common type of genetic testing done on embryos today.
To make this super simple, let's think about it like this. Imagine an embryo's DNA is a full set of encyclopedias. A healthy human should have 46 volumes. That's 23 pairs. PGT-A is basically the librarian who goes in and counts every single volume to make sure the set is complete. No extras, none missing. An embryo with the right number, that's called euploid.
So who is this test for? Well, it's often recommended for women over 35, or for people who have been through the absolute heartbreak of multiple miscarriages, or for couples who've had several IVF cycles that just haven't worked. The idea is that a chromosomal problem could be the reason things haven't been successful.
And this chart, wow, this really shows you why PGT-A is used so often. Look at this. If you're under 35, about 65% of your embryos are expected to be chromosomally normal. But watch what happens. By the time you're 38 to 40, that number has dropped to just 34%. And over 43, it's a staggering 5%. This is the biological reality PGT-A is trying to help us navigate.
But, and this is really important, it's not the whole story. Big medical groups like the American College of Obstetricians and Gynecologists have pointed out that while PGT-A is used all the time, the jury is still out on whether it actually improves live birth rates for everyone. It's a powerful tool for selecting embryos for sure, but it's not a treatment that fixes them.
Okay, so if PGT-A is about doing a broad head count of all the chromosomes, our next test, PGT-M, is like a sniper. It's incredibly specific. The M here stands for monogenic. We are no longer counting the books, we're looking for one specific word on one specific page.
Right, back to our encyclopedia analogy. PGT-M is for when you know there's a really critical typo, a mutation, in, say, volume 12, on page 84. This test is designed for people who already know they're carriers for a specific genetic disease, something like Huntington's or cystic fibrosis, and they want to make sure they don't pass it on.
And let me tell you, this is not an off-the-shelf test. PGT-M is a serious, customized process. It all starts with genetic counseling to pinpoint the exact mutation running in the family's DNA. From there, a lab can spend weeks, even months, building a custom probe, a unique DNA fingerprint just for that family's gene, before a single embryo can be tested.
But here's the catch. An embryo could get a perfect score on the PGT-M test, no single gene disorder, but it could still have the wrong number of chromosomes overall, which is what PGT-A checks for. This is why there's a big debate in the field about whether it's best to do both tests together.
And that brings us to our third test, PGT-SR. The SR is for structural rearrangements. Now this gets into an even more complex type of chromosomal problem. It's not about the count, and it's not about a single gene. This is all about the large-scale architecture.
So let's visit our library one last time. For PGT-SR, imagine opening up the encyclopedia set and discovering that a whole chapter from Volume 9 has been ripped out and stuck into Volume 17. All the information is still there, technically, but it's jumbled and in the completely wrong place. That's a structural rearrangement.
So who needs this? It's for people who carry something called a balanced translocation.
Now, the person carrying it is usually perfectly healthy because, just like in our analogy, they have all the right genetic info. But the problem is they have a much higher risk of creating eggs or sperm with an unbalanced amount of that information, which sadly often leads to infertility or repeated miscarriages.
And you can really see how far the technology has come right here. The old method, called FISH, was done on day 3 embryos and was honestly pretty inaccurate. But today we have next-generation sequencing, or NGS. It's done on a more developed embryo and is way more accurate. It can spot tiny rearrangements the old tech would have just completely missed. It is absolutely the standard now.
So there you have it, the 3 main types of PGT. But of course, the science never stops. The whole field is moving at lightning speed, and there are still some pretty big challenges to solve, and some really exciting innovations just around the corner.
One of the biggest challenges for all types of PGT is something called mosaicism. This is where an embryo isn't uniformly normal or abnormal. It's a mix. The problem is, the biopsy only tests a few cells from the outer layer. What if those cells don't match the inner part that actually becomes the baby? It leads to this incredibly tough question. Could an embryo we label as abnormal actually have been okay?
So, to try and get around these issues, the real holy grail of the field is non-invasive PGT. Right now, we have to physically pull a few cells out of the embryo, which has risks. The future, we hope, is to simply analyze the tiny bits of DNA the embryo naturally sheds into the liquid it's growing in. No biopsy, no risk.
But we're not there yet, not by a long shot. Non-invasive testing has some major hurdles to clear. For one, there's barely any DNA to work with. There's also a big risk of contamination from the mother's DNA. And it's still not great at detecting mosaicism. So it's got amazing promise, but it needs a lot more work before it's ready for prime time.
So you see, PGT gives us this unbelievable window into the very first days of life. But it also forces us to ask some really profound questions. As our ability to read this genetic blueprint gets better and better, the amount of data we can get is just exploding. And the real challenge going forward isn't just about getting the data, it's about figuring out how to use it wisely. It's about finding that right balance between what we can know and what we should do. It really is the intersection of data and destiny.